Hey everyone, welcome to our next video. Heading over to our notes. This one is 4.4, so our last section in chapter 4. And it's just more equations, but now we're doing different types. So this is trigonometric equations of quadratic type. This one can be a little tricky for students because first we have to remember what a quadratic equation is. So a quadratic equation is something of the form y equals ax squared plus bx plus c, where the a cannot be 0. So that's like kind of the basic sort of definition of a quadratic equation. That's what you may have seen in like an algebra class or, something like that. So with this section, what we're going to have to do a lot of the time is like factor or something along those lines, basically solve a quadratic before we actually even do the like trig part of the equation or of the like solving. So I did review like some factoring and stuff like that in 3.1. So if you start to struggle kind of with the factoring and stuff that I'm doing, I would maybe recommend going back over there and maybe checking those out, or maybe even looking up just some basic like algebra videos. So I'm going to try to take it a little slow. So one way to solve a quadratic is to use the square root property. And so I'm just going to come up with like a little algebra example to hopefully remind you of what this is. So if you have like x squared equals 1, usually with something like this, we would just square root both sides. And you have to be careful because remember when you take square roots, it needs to be plus or minus. So this becomes x is equal to plus or minus 1. So we can do that, but instead of maybe x, it's like a trig equation. So let's look at our example 1. I'll say solve for x within, we'll say 0 to 2 pi. So for this one, we're only going to be looking for values of x between 0 and 2 pi. So we're not going to need to like leave k on our final answer, if you remember from our previous chapter 4 sections. So our first one, let's look at, we'll do sine squared x is equal to 1. And we'll do another one, but I don't want to run out of space. I am going to go ahead and draw my coordinate plane over here that I always reference back to. And I'm going to do my table as well, because we are definitely going to need those for these problems. And you can have it in radians or degrees. I went ahead and wrote it in radians at first. The reason I did that is because I see that this 0 to 2 pi here means that I'm probably going to want to leave my answer in radians as well. But I've also mentioned to you that that's not something I'm super picky about. So 30, 45, 60. In radians, that is pi over 6, pi over 4, pi over 3, in case we need to see those again. So 1 over 2, root 2 over 2, root 3 over 2, and then cosine is the opposite. All right, so we can go ahead and get started on our problem now. So for this one, just like what we did up here, I'm just going to square root both sides. And that'll cancel out the squared. But be careful, this is plus or minus when you take a square root. So this will become sine x is equal to plus or minus square root of 1 is just 1. So now I can kind of separate this into two different equations. I have sine x equaling negative 1, and then I also have sine x equaling positive 1. So if I solve the first one, now they just look like 4.1 problems. I'm not 4.1, sorry, 4.2. So sine x equals negative 1, that's going to happen down here at 270 degrees, or 3 pi over 2. So my answer here is 3 pi over 2. I like to always add in the plus 2 pi k and then just get rid of it at the end if I need to. Sine is equal to 1 at pi over 2, or 90 degrees. And so if the problem had said for all values of x, we would be boxing this in. But it did not, so we'll just write out our values that we want. So just pi over 2 and 3 pi over 2. Let's do another one of these. This one we'll do cosine squared x is equal to 1 over 4. And it could also maybe be written as, let's maybe make this one a little bit trickier to look at. Let's do minus 1, and then we'll put 4 here, equals 0. Just to kind of change it up a little bit. So for this one, I would want to get the cosine squared alone first. So to do that, I can move over that 1 and then divide by 4. So I didn't actually change the problem. I just wanted to show you that sometimes you may need to manipulate a little bit. Now we square root both sides. Be careful because this is plus or minus. So this will now become cosine x is equal to plus or minus square root of 1 will just be 1, and the square root of 4 would be 2. So again, I'm going to go ahead and split this into two equations. Cosine x equals negative 1 over 2, and then cosine x equaling positive 1 over 2. So I'm just splitting it up because of that plus or minus. So I know for both of these, my reference is going to be, let's see, cosine 1 over 2, so pi over 3, or 60 degrees. The difference is really the quadrants. So cosine is going to be negative in quadrants 2 and 3. It's going to be positive in quadrants 1 and 4. So for the negative 1/2, I would get, so remember this is pi, or 3 pi over 3. So that's going to give me 2 pi over 3 plus 2 pi k. And then I also get the answer in quadrant 3 of 4 pi over 3 plus 2 pi k. For my positive 1/2, I get pi over 3 plus 2 pi k. And for the last one, I'll get 5 pi over 3 plus 2 pi k. And I'm getting that because this is 2 pi, or 6 pi over 3. So subtracting pi over 3 would give me 5 pi over 3. And we can also write this in degrees if you would like. So if it had said for all values of x, I would be boxing in all of these. Since it didn't, I am going to go ahead and just sort of list out the values. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 were all acceptable answers for this one. If you go ahead and check this out in radians, I'm sorry, not radians, in degrees, we did radians. In degrees, that would have been 120, this would have been 240, this would have been 60, and this would have been 300. So in degrees, this would have been 60 degrees, 120 degrees, 240 degrees, and 300 degrees. So those are some examples of using like the square root property. Now we're going to talk about factoring. So factoring is kind of the go-to way of solving quadratics. I'll remind you what we're kind of looking at here. Some algebra examples very quickly. If I say like x squared oh, it's hard to just make one up on the spot. Plus 5x plus 6. I don't know, something like this. So we would put this into two sets of parentheses. It would be x plus 2, x plus 3. So then we'd split it into two functions, x plus 2 equals 0 and x plus 3 equals 0. Some things to remember whenever you are factoring is that you need to be equal to 0 to be able to start factoring. Another quick example of factoring, if I have x squared minus x, I can factor out an x, and I'd be left with x equals 0 and x minus 1 equals 0. And if you want a better explanation of those, I would go ahead and check out 3.1 because I definitely explained those a little bit more in that section. And then also you have this example that is the difference of squares. So a difference of squares, x squared minus 4 would become x plus 2, x minus 2. So in all of these, we have to always be equal to 0, so that's a huge part of it. And yeah. So let's go ahead and do some examples that actually have like the trig in them. So I'll just say solve for x in the interval 0 to 2 pi. And I'll try to do one kind of each of the examples that I showed so far. So we'll start off with a tangent one. Let's do tangent squared x is equal to tangent x. Oh, sorry, sorry if that sounded weird. I yawned. I don't know if it was loud. So our first step is one, it's good to notice some things. So something I'll see a lot of students do with a problem like this is they try to take the square root. The problem with doing that is it does cancel out this one, but then what are you supposed to do over here with square root of tangent? You know, it just kind of leaves you with not very many options. If you see that you're having multiple of like a trig function up here, it's probably going to be best to try to factor it out to the front, kind of like this case, like factor out a greatest common factor. So what we can do with this one is move tangent over to the other side so that we have them both on the same side. At this point, I can factor out a greatest common factor. So in this case, that would be tangent. And I'd be left with tangent x minus 1. Then I can split up because anytime you have something multiplied by each other, you can set them both equal to 0. So this would become tangent x equals 0 and tangent x minus 1 equals 0. And so I'm going to solve these separately. Let me go ahead and grab my table from earlier. I'm going to write it down with us. That way I can kind of reference back to it while I'm doing a problem. Alrighty, here we go. Okay, so over here, the tangent x equals 0. I'm looking for where tangent is going to equal 0. So remember that tangent is sine over cosine, or y over x. So if I do tangent over on this graph right here, I would have 0 over 1, so 0. This one would be undefined. This one would be 0, and this would be undefined. So I'm just taking the y value over the x value since that how tangent is defined. So what I'm seeing is tangent is equal to 0 at 0. And remember with tangent, it has a period of pi. So it'll just be plus pi k. For the second one, I would make this tangent x equals 1. And then I'm looking for where does tangent equal 1? Well, if I add tangent to this table, this is 1 over root 3, 1, and root 3. So it's happening at pi over 4 as my reference. And tangent is positive in 1 and 3. So this is going to be pi over 4 plus pi k. Now I want to reiterate to you, if it had said for all values of x, this would be our final answer. Like we'd be boxing this in and that would be it. It didn't say that though. It only wants between 0 and 2 pi, so I'm going to have to actually write out all the values that will satisfy. So 0 satisfied, pi over 4 satisfies, pi satisfied, and then quadrant 3, reference of pi over 4, would be 5 pi over 4. Now I also want to talk about this in degrees. So this would have been 180k. This would have been 45. So this would be 0, 45, 180. And then quadrant 3, I would do 180 plus 45 to give me 225. So those would be my angles if I did this question in degrees. Sometimes I've also seen students with this one, they try to like divide by tangent and just get rid of it. What that does is it leaves you with, it actually leaves you with this equation. So you'll be able to get part of your answer, but you would miss out on this equation, so you won't be able to get full credit for that. So be careful. Alrighty, I'm going to do another one. Let me go ahead and bring my table down with us as we work through these. So let's do part B. Um, Now, give you a little bit of information, a little bit about the test. As you know, I always try to structure test 1 and 2 to be done with no calculator. What this means is there's only so many of these that I can give you. Like, I have to give you something that factors nicely. I'll talk about what I mean by that probably after this example. So, for this example that we're about to do, I would say this would be a really good one to study ones like this when you're thinking about like test questions. So this one I'm going to do sine or cosine. Let's do sine. I don't know. It really does not matter. Sine or cosine. This one I'll do sine. 2 sine squared x equals 3 sine x minus 1. So when we see this kind of like decreasing pattern here where we've got a sine squared, we've got a sine by itself, it's very likely that we're going to be factoring this one. So I can move everything to one side. And then we can factor. Now in 3.1, I talked about like if it's a lot to kind of see this with sine, you can always replace it with another letter temporarily and factor it that way at first. You're welcome to do that here as well. So let me show you what I mean by that. So in 3.1, I said something like let y equal sine x. Then we can see that it would be 2y squared minus 3y plus 1. And maybe that would be a little bit easier to factor, just not seeing it with the sign. So when I factor this, two things that multiply to get to 2y, well, to multiply to get to 2, it's just 2 and 1. That's my only option. So this is going to be 2y and y. Multiply together to get to 1. My only options are 1 and 1. And then my signs need to be the same because it's positive here and negative here, so they're both going to be negative. So this one is going to become, I'm going to go ahead and put my sign back in. So I get 2 sine x minus 1 times sine x minus 1. And you may just be able to go straight there, but maybe replacing it could be helpful, so I do like to show it. Now I'm going to split into two equations. Solve them for sine x. So here I get sine x equals 1/2. So then I get sine x equals 1. Sine x equaling 1/2. So my reference, if I go and look at my table, my reference is 30 degrees or pi over 6. And sine is going to be positive in quadrants 1 and 2. So I need both of those answers with a reference of pi over 6. For sine x equals positive 1, that's happening up here at pi over 2. So this one's a little quicker to solve. It would be pi over 2 plus, don't forget the 2 pi k. Just in case it wants all values, you always want to write that and then maybe just get rid of it at the end if you don't need it. Sine x equals 1/2, so my quadrant 1 answer is pi over 6 plus 2 pi k. And my quadrant 2 answer is going to be 5 pi over 6 plus 2 pi k. And just a reminder of how I'm getting that. Let me draw this a little bit bigger. This is pi, or I can write it as 6 pi over 6. My quadrant 2 has a reference of pi over 6, so I'm doing 6 pi over 6 minus pi over 6 to get 5 pi over 6. Now for my final answer here, I do not want all of these because it just said from 0 to 2 pi. So I'm just going to write out my answers. And that's it. But I will say that sometimes these can just be intimidating, I think because they involve algebra at the beginning. And so it's kind of hard when maybe you aren't super strong in algebra to even get to the trig part of it, because all of this is algebra. And then you don't actually even get to the trig until this line right here. Kinda. Even more like when I started writing in blue. That's really when we started doing trig. Up to that point was pretty much just algebra. Alrighty. I'm gonna go ahead and bring this down with me. This next one, I'd like to show you one where maybe you have a sine and a cosine in the problem. And like seeing what we can do with that to fix it. So this one we'll do 2 sine x cosine x plus cosine x is equal to 0. So this is one where we will try to take out a greatest common factor. So you always want to be on the lookout for that. If there's maybe anything that both of your terms have that you can factor out to the front. So in this one, since they both have a cosine, I can factor a cosine out to the front, and I'd be left with 2 sine x plus 1. Now I can split into two different equations. And for this one, I'll go ahead and do it in degrees, just to show you that. I find that students usually do prefer degrees, so I don't mind. Either one is fine. So cosine x equals 0, that's happening in two spots. Pi over 2 and 3 pi over 2, or 90 and 270. Remember, cosine always goes with the x part of the coordinate. So this is going to be x equals 90 degrees plus 360k. I almost wrote 2 pi. And then x equals 270 plus 360k. You want to make sure if you're in degrees, you write everything in degrees. For sine x equals negative 1/2, I have a reference of 30 degrees, but sine is going to be negative in 3 and 4. So here I'm going to get, for quadrant 3, 180 plus 30 would be 210 plus 360. And then in quadrant 4, it would be 330 plus 360k. But if it only wants certain, so if it says for all values, then you want to go ahead and box all of this in. But if it says like only between 0 and 360 or something like that, we would write it out. So for this one, let's say I say x in 0 to 360, something like this, then you would want to make sure you write out each individual answer. All right. Next, I want to get into like using some identities to help you solve equations. So I'm going to go ahead and do, this would be example 3. So I'm still just going to say solve, and then I'll say use an identity to help. The homework is not usually going to tell you when to use an identity, but I'm telling you that for all of these equations that we're going to look at, we are going to be using identities to help us. On the test, I usually hint towards needing to use an identity. So for the first one, let's do sine 2x minus cosine x equals 0. And it could also, you know, have the cosine on the other side or something like that to start off with. Let's do that, actually. Sorry, I changed my mind. I want it to equal cosine x because I think that makes it a little bit more work for you, so maybe a little harder. And I'll do a few of these. So for this one, here's my issue. One, I have sine and cosine, which is not good. And then also I'm seeing sine 2x, so I'm seeing like different stuff in the parentheses. Well, there is an identity, so I would usually at this point maybe go to the identity sheet and see if there's anything that can maybe help me out that I could like replace one of these functions with. There is an identity from your identity sheet that says sine 2x is equal to 2 sine x times cosine x. So what I can do is replace that here. And I can say, okay, let's do 2 sine x cosine x. And then it's equal to cosine x. So I didn't change that side. I just changed sine 2x to 2 sine x cosine x. At this point, if you start thinking, oh, I can divide both sides by cosine, you never ever want to divide by an entire function. You can divide like by numbers and stuff, but not a whole function. You'll miss out on some answers that way. What we can do instead is we can move everything to one side and then factor out a cosine to the front. So this one is actually really similar to the example that we just did a second ago. I just maybe showed like what if it starts out a different way. So what if you have a little bit more stuff going on? So this would be factoring out a cosine x. I'm left with 2 sine x minus 1, split into two different equations. Do some algebra. So here's my two equations. Now I can do trig. So up to this point, I've only done algebra. Well, kind of. I guess using the identity was using some trig. The factoring part was just algebra. So cosine x equals 0, that's going to happen at 90, and it also happens at 270. For sine equaling a half, that's going to happen at a reference of 30 degrees, and sine is positive in 1 and 2. So it's going to be 30 degrees plus 360k, and the quadrant 2 would be 150 degrees plus 360k. And so let's say for this one, I said all values of x. Then I would just box in all of this stuff. This one on the side here can actually be condensed a little bit. It can be written as 90 plus 180k. Since they, like if you add 180 to 90, you'll get 270. And you can keep going back and forth, like top to bottom, like here, here. Like when they're perfectly across from each other like that, you can technically use 180k. I did talk about that in 4.2. I talked about like cosine or sine equaling 0. It's kind of the exception to how you write your answer. Um, you can write them separate or you can condense it into one. I'm not really picky about it, but it is something to keep in mind for the homework. Let's do another one. This one says, oh, I had it. Okay, here it is. Tangent 2x plus tangent squared x is equal to secant squared x minus 1. And let's say for this one, we'll look for x, and we'll say 0 to 360 for this one. So this one's got a lot going on. One, I've got the fact that the parentheses are different. That's a whole thing. I also noticed that I have tangent and secant in here together. Now, I do notice that I have more tangent than secant. So I'm thinking maybe there's a way I can get rid of the secant. And so there is an identity, and my other hope is that when you start seeing like tangent squared, the number 1, and then maybe also see secant squared, my hope is that you would remember that there is an identity that kind of looks like that. So there's an identity, tangent squared x plus 1 equals secant squared x. We use this identity for the first time in 3.1, excuse me, is when it was given. It comes from the fundamental identity. And we used it a little bit in 3.2 as well. So if I make this look kind of like what I'm seeing, I do notice that maybe I can get rid of this. So if I move that one over, I can see that tangent squared x is equal to secant squared x minus 1. So what I can do is replace secant squared x minus 1 with tangent squared. So I'm going to do that now. So I have tangent 2x plus tangent squared x is equal to, and now over here I'll have tangent squared x. So that's nice because it at least gets me all with like tangent, which is cool. Then if I combine like terms here, I can subtract both sides by tangent squared x. What happens though is that they cancel out. So I'm just left with tangent 2x equals 0. And that's it. That's all I've got. I need to bring down my table and stuff. Here, let me do that. Because I'm about to reference it, so I want it in my area. Okay. So the reason like you might be like, well, earlier we couldn't like cancel out, it's because earlier like I was warning you against trying to like divide everything by something. So you don't ever want to divide by an entire function. However, if while you're combining like terms, they happen to like subtract by each other or something, that is okay. So different cases. Now, this problem has become very similar to 4.3 at this point. So I'm going to treat it as such. So I usually like to let my parentheses equal something else whenever I have something like this. So I'll let 2x equal, let's just say like alpha. So then I have tangent alpha equals 0, and that brings it to a 4.2 problem. So now tangent alpha equals 0. Well, that's going to happen at 0 and 180. So I get alpha equals 0 degrees plus 180 degrees k. Remember, for tangent, you don't ever have to write out like multiple answers. Usually you can condense it into one by using plus 180k instead of 360. But be careful, I got to put that 2x back in. So this becomes 2x equals 0 degrees plus 180 degrees k. If I divide both sides by 2, I'm going to get x equals 0 degrees plus 90k. If it said for all values, we would just box this in. Technically, you can get rid of the 0, but I hope you get the point. Since it wants it in an interval, I want to make sure I write everything like individually that would work. So I'm going to get 0 degrees. If I add 90 to that, so 90 would work. Add it again, so 180 will work. Add it again, so 270 will work. Be careful. See how there's a parentheses right here on that 360? I didn't mean to erase. That parentheses right there means that we do not want to actually get to 360. Now, if on the homework you notice that it has a bracket, then 360 would be included in this answer. But in our case, we had a parentheses, so we are not going to include 360. So be careful about that. Sometimes that's like a pretty small, I think that's like a tiny mistake. I probably wouldn't even take off for something like that on the test. I would just maybe make a note, of it, but that's not really something I would take off for. But the homework will catch you on that. So this just goes to show you that sometimes you can use identities even when solving equations to maybe help simplify the equation a little bit. There's some really good examples in the textbook as well. I don't know if you've ever really looked at the textbook, but I will say that I definitely take test questions from the textbook. So if maybe you have done the My Math Lab and you found that either you use the example for almost all the questions, you probably need more examples and you might want to check out the textbook to do some more practice. If you find that you did the homework and you got through it, but it was just a hassle, just go ahead and check out the textbook a little bit. Even if you did the the section well, all of them, you might still want to check out the textbook and at least take a look at some of the problems. Because a lot of these, I believe the last like 2 or 3 examples I've done actually, maybe even 4 of them. I mean, some of them are actual examples from the book, like they explain how to do them. And some of them I just take from the exercises. Like I like them, so I just pull them. I think that's an example for this last one that we did, this one. I took this one from the exercises. This is actually one that I did in my notes. It's like a review problem or something that I had written one day. So definitely good to maybe look at that to get some more problems and ideas. Okay, at this point, I want to tell you that what we have done so far are examples that you can expect to see on your test. For my next example, this is not something that I would test on. It is on the homework, so I like to show it. And I do think that if you can be successful in these harder problems, then you'll be good for the test. But I don't usually like test on these, mostly because it's hard to make them possible like without a calculator. So I actually picked these from the homework, the ones that I want to do. And again, the issue is that you need a calculator to do them, and I don't like that, you know. I want this test to be able to be done with no calculator, so it kind of limits what I can give on the test. So what example number are we on? 4. So example 4. So I'm just going to put a note here. We will need a calculator for these. And so I'm just going to say solve for values between 0 and 360. So for my first one, I want us to do tangent squared theta minus 3 tangent theta minus 1 is equal to 0. So this one looks like something that I would factor. The problem with it is that it can't be factored. If you can't factor it, and it looks like this, where like you would try to factor, like you don't really have that many options. This is one that you actually have to use quadratic formula. So I'm going to remind you of quadratic formula. You have whatever your variable is. So in our case, it's like, I'll write it like this. So if you have like 0 equals ax squared plus bx plus c, quadratic formula is x equals negative b plus or minus the square root b squared minus 4ac divided by 2a. I guess technically I could test you on something like this if I just wanted to be completely mean to you, but I don't. I don't wanna do it. So I need to like apply this problem to kind of the algebra. So I don't have a number in front of the tangent. That means there's an invisible 1 there. So I'm seeing that my a is equal to 1, my b is negative 3, my c is negative 1. So I'm going to plug this in. So my variable here is um, really not even just theta, it's actually like tangent theta, because that's what I'm seeing instead of x. So I have tangent theta equals negative negative 3 plus or minus square root negative 3 squared minus 4 times 1 times negative 1, all divided by 2 times 1. Keep bringing down my tangent theta. I get 3 plus or minus the square root. This is going to give me 9 plus 4 divided by 2. So I get tangent theta is equal to 3 plus or minus square root of 13 divided by 2. Wow. At this point, I can split this up into two equations. I have tangent theta equals the plus 1, and I have tangent theta equals the minus 1. To do this one, you'll actually need the general form of tangent. I gave that in 4.2, and it's only because we have to use the calculator. So that's why I don't really like to do ones like this on the test. So my answers here, I have theta equals tangent inverse 3 plus root 13 over 3. So I'm going to have to type that in. Sorry, not over 3, 2. Over here, I would have theta is equal to tangent inverse 3 minus root 13 over 2. So I need to type both of these in, and I'm going to do that really quick and see what I get. If I know where my calculator is on my desk, here it is. So I'm typing these into my calculator. So let's see. I get 3 plus root 13 over 2. Plug that into tangent inverse. This gives me theta is equal to 73 point. Let's see, this one is asking for nearest tenth, so I'll go ahead and just write it like that. Now we want to always be careful here because remember that it's always plus 180k for tangent. And I just want to check that because if I am able to add 180, I'm going to have to include that in my answer. Let me do the other one as well. 3 minus square root of 13 divided by 2. Oh, interesting. This one gives me a negative angle. That's okay. Negative 16.8 plus 180 degrees K. Alrighty. Now here's where we have to be careful for this one. I need to find from 0 to 360. See? So I'm going to have to figure out which ones will fit. So 73.2 fits. If I add 180 to that, let's see what I get. 253.2, okay, so that one works. If I add 180 again, 433, so that one is not going to work. So that's it for the first equation. For my second one, negative 16.8 is not going to work because it's negative. It's smaller than 0, so that one's not going to work. If I add 180, I get 163.2. That one will work. Let me put a note here of what these are. So this one is 73.2 plus 180. This one is negative 16.8 plus 180. Try to add 180 again. See if it's less than 360, and it is. I would get 343.2. And so let me put a note here. This one is 163.2 plus 180. And those are all the answers that we're going to be able to get. Now, I do want to type these in really quick into the homework problem just so that I can check it and make sure that I didn't do anything wrong either, because this is kind of a wild problem. I wonder if y'all can hear me like typing. Alrighty, moment of truth. Okay, it gave me a check mark. It said good job. Yay. So that is a very interesting problem. Again, not really something I would throw at you on a test because I do think it's good. I think it's great for you to know how to do stuff like that. I just realistically like to make the test no calculator. This is another one that I don't usually put on the test, but it is a great one for us to do, partially so that you can just kind of work through the homework, get some experience. So this one's example, I don't know what number we're on. 6, 5? Okay, 5. This one we won't need a calculator. We're gonna solve for x in 0 to 360. So don't need a calculator for this one. It says cosine theta minus sine theta is equal to 1 minus square root of 3 over 2. This one uses a method that you actually use a few times in this section, like while you're going over problems. It's where you actually have to um, square both sides for this one. The reason is because there's no identities that I can use. There's no factoring that I can do. Like, I'm stuck, really. I'm just stuck. And I do know that if I can square the cosine and the sine, I may be able to use some identities after that. So we're going to actually square this one. So this one's going to be cosine theta minus sine theta times cosine theta minus sine theta, I'm going to have to distribute that out, is equal to 1 minus root 3 times 1 minus root 3 over 2 squared would be 4. So if I simplify the left side, I get cosine squared theta minus sine theta cosine theta minus sine theta cosine theta. Might run out of space. Plus sine squared theta is equal to, and I'll just kind of bring down that side as I have more room. So this is cosine squared theta minus 2 sine theta cosine theta. I'm just combining like terms right there, combining those together, plus sine squared theta is equal to, and now I'm going to do the like right side, like simplify that one. So that would be 1 minus root 3 minus root 3 plus 3 over 4. I'm continuing to simplify. I'm not using any identities yet because I don't want to. I want to simplify before I start doing that. So this is going to give me 4 minus 2 root 3 over 4. Simplifying further, y'all are probably like, oh my gosh, this is crazy. It kind of is. This would become 2 minus root 3 over 2. Wow. Now I'll use some identities. I do see cosine squared plus sine squared. So that identity tells me that it equals 1. So that's just going to become 1. I can also replace this 2 sine theta cosine theta. So 2 sine theta cosine theta is equal to sine 2 theta. So I can do 2 replacements right now. So that's what I'm going to do. I get sine 2 theta. Be careful, it's negative, so I'm going to keep my negative. So I kept that. Plus 1, replacing that cosine squared plus sine squared with 1. And then on the other side, I have 2 minus root 3 over 2. I can simplify further. This becomes negative sine 2 theta is equal to, over here, I'm going to do a few things right now. I'm subtracting 1 to the other side. So I need to be able to reduce this. 2 over 2 minus root 3 over 2 minus 1. 2 over 2 is just equal to 1. So the 1, this is actually going to cancel each other out. I'm left with negative sine 2 theta is equal to negative square root 3 over 2. I can get rid of the negatives. I get sine 2 theta equals square root 3 over 2. Wow. I can't imagine, I'm looking like at the example a little bit because I want to see how they explain it. And let me just tell you, it's crazy. The way that they are explaining this is so like bonkers to me. Some lines make sense and some are just like, I don't know, they just don't really show any work at all, you know? They're just like, here you go. And you probably look at this and ask like, I have no idea what they just did. And I would agree with you. I think it's really hard to read through like what they're doing here. All right, so now we're dealing with something that looks more like a 4.3 problem. So I'm going to replace 2 theta with like x. So then I have sine x equals square root 3 over 2. This is not too bad to solve. Sine is equal to square root 3 over 2 at a reference of 60 degrees. It's going to happen in quadrants 1 and 2 because that's where sine is positive. So here I'm going to get x equals 60 degrees plus 360k. And then for quadrant 2, I'll get 120 degrees plus 360k. Remember though, I need 2 theta to be in there, so I am going to replace that back in. So I get 2 theta is equal to 60 degrees plus 360 degrees k. 2 theta equals 120 plus 360k. Divide by 2. Get theta equals 30 degrees plus 120k. Theta equals 60 degrees plus 120k. We got to be careful here because we only wanted values of theta between 0 and 360, so I'm going to write those out. So 30 degrees works, 60 degrees works. Let's see, 30 plus 120 gives me 150. Oh, I made a mistake here. I wrote 120 instead of 180. My bad, my bad. I don't know why I did that. I guess I divided by 3 on accident. I don't know. I don't know. It's too crazy of a problem. So 30 plus 180, let's see, that gives me 210. 60 plus 180 is going to give me 240. And then I can't go any further than that because I'm going to start getting bigger than 360. Here's the issue. I can't believe we're still doing this problem. Um, as we squared both sides, we run the risk of having answers that are not allowed. This question is crazy. Count how many times I've said that. So something that happens in algebra is there's something called like extraneous solutions. It often happens when you do something like squaring both sides. Like if you maybe remember solving like square root equations or something, you had to check for extraneous solutions. We can get those whenever we square both sides of a trig function. So what I need to do right now is I need to check all of these answers by plugging in to the original equation. So you will have to check each and every single one of these answers. Now, I would just use a calculator for that, and I would just see what I get. Like I would see, um, so I'm going to have to check them into cosine theta minus sine theta equals 1 minus root 3 over 2. 1 minus root 3 over 2, let's see what that is in decimals. Okay, it gives me negative 0.37. So that means that if I plug any of these in as theta, it should equal negative 0.37. So let's see. I'm going to go ahead and check 30 degrees first. So 30 degrees, I'm going to go ahead and plug it in and see what I get. So cosine of 30 is going to give me 0.8 minus sine of 30 is going to give me 0.36. Okay, here's the problem. I get, if I plug in theta equals 30, I get 0.37 equals negative 0.37 because this side is not changing. Okay, so that's not going to work then. 30 degrees is not a valid answer. So that one is not working. What about if I check 60 degrees? This one, let's see, cosine of 60. And I want the decimal answers right now, so that's why I'm doing this one. I think I said earlier that we didn't technically need a calculator for this one. I mean, we don't, but it makes it a lot easier when you're checking your answers. So technically, you do not need a calculator for this one. But when you're checking your answers, it's kind of hard to do it without. So this one, I get that the two sides are equal. So this one is good. So 60 is a valid answer. So I'm going to go ahead and box that in. If you plug in 210, you'll find that it doesn't work. Oh wait, just kidding. It does. I thought it was, I got them backwards for a second. This one works, so that's a good answer. And then if you do 240, that one does not work. Yeah, that one gives you 0.36. I'm sorry, 37. So it's all about the signs. So for this one, your only correct answers are 60 and 210. All right. This question came from number 10 on the homework. I think it's crazy that you're getting such hard ones so early. Usually it's like later in the section before you get crazy stuff like that. Um, I really do think some of this section is kind of wild. I'm just gonna be completely honest with you about that. Like in the My Math Lab, it's kind of intense. If you're able to do them, I think that's great. I think you can take some good stuff from this. Like for instance, when we got to like here, I think that that became like a good problem. But all the way up to that point and then after is just not really like the checking the answers. That is not really stuff that I'm going to expect from you on your test. So I just really want to be honest with you about that. And um, yeah, just just know that some of this section is a little intense. I think if you can do it, that's going to be amazing. I would focus on problems a little bit more similar to what I did on example 1, 2, and 3. Those examples are a bit closer to what you'll actually see on your exam. Um, just remember that in the syllabus, I do allow the homework to be at like 90% to get your full points. So the reason I do that is because I know that there's some hard problems like this in there. So just something to keep in mind. All right. Well, I hope that you stuck with me this far. Um, if you didn't, I don't blame you. And if you did, awesome. I hope that it was all right. But okay, I'll kind of just wrap up now. I hope y'all are having a good day. I hope you have a good rest of your week because this is the last one I'm going to post this week. But yeah, okay. Good luck on test 2. I know that should be on your mind if you're finishing this section. Hopefully, it's not too soon. Hopefully, you get still a day or two to study. I hope. I hope. But yeah, I'm wishing you good luck, and I will see y'all in our next video. Bye bye.